Hello, and welcome to German Nature, the channel that encourages us to be inspired by nature for innovation. For our first episode, I'm here with biologist and engineer and professor at the University of Akron, Dr. Henry Astley. Hi Henry, how are you doing today?
Good, yourself?
I'm doing well, thank you. So here at the university, Henry is most well known for his research on snakes. Can you tell us a little bit more about that?
So I've been working on snakes for as long as I've been in academia. I've always been interested in how these elongate limbless organisms move and how we can harness the power of their movements to design better robots and better devices for human use. The limbless body plan is extremely common in nature, with snakes simply being one of the most successful examples. So they make an ideal model organism for study.
Great, great. And what is it about snake locomotion that has applications for biomimicry?
Well, snakes actually have a variety of different modes of locomotion that are triggered not by different speeds, like when a horse walks, runs, or gallops, but by differences in terrain. So snakes will use a different gait in a tunnel versus in a grassy field versus across sand dunes, or when swimming, or when moving through an extremely narrow tunnel. Most snakes are capable of at least the classical three: lateral undulation, or what's often referred to as slithering, concertina locomotion, the sort of inchworming motion they do in tunnels, and rectilinear, a skin-based form of locomotion that they can use either in very narrow tunnels or to move silently through the undergrowth. A few species are also capable of sidewinding, which they use to move on loose granular substrates like sand or tidal mudflats. But only 8 species are known to be able to sidewind. This gives them a degree of versatility that you don't actually see in a lot of other limbless organisms, and might be one of the reasons why this group of animals has been so incredibly successful in terms of the sheer number of species and global distribution that they have. If we can replicate these behavioral modes in robots, we should be able to achieve, ideally, similar behavioral performance in robots and enable them to move through the diverse environments that snakes inhabit. Forests, deserts, rock piles, all sorts of things like that.
Great, so these would be like exploration robots and things of that sort.
Yes, exploration is certainly one of the aspects. Rescue is another. If a building collapses and you have this large rubble pile, snakes are excellent at moving through tiny, confined spaces. And theoretically, a snake robot should also be similarly excellent at moving through these sort of crevices in order to find survivors.
And there's certainly something very sci-fi about being rescued by a robot snake. I think that's really cool.
This is the sidewinding snake robot, which emulates the gait of a sidewinder based on some discoveries that we made of how sidewinders coordinate their locomotion. So in spite of it appearing to be quite complicated, this motion is really just a pair of waves traveling down the body, a vertical and a horizontal one. The robot just has a horizontal series of motors and a vertical series of motors moving through 2 different waves, offset slightly. And this produces a similar mode of locomotion to sidewinding. We're still trying to work out the ideal coefficient of friction for this. So we still have a little bit of slip. Robots are unfortunately never quite as good as the real animals, because they haven't had 150 million years to evolve into it.
Sure. So all these little segments are 3D printed, is that right?
The connectors are 3D printed. The rest of it is simply servo motors.
Okay.
So it's mostly 24 servo motors connected together in series, Dynamixel XL320s. And these motors actually allow me a great deal of control, because I can change how stiff the control is. So in these portions that are on the ground, it resists attempts to bend it, whereas the portions that are lifted are much more compliant and flexible. And the goal with this is eventually to have a robot which can negotiate obstacles without having to rely on complex computations of where the obstacle is, but instead simply just bends as its body naturally would, without having to think about things and recalculate body positions. And these regions can move down the body with these servomotors. Most servomotors don't have the ability to modulate themselves this way.
And that's indicated from these lights here.
Yes, the green lights are stiff, the red lights are compliant.
Okay. So it sounds like your research has to do a lot with both biology and engineering.
Biology has always been the central source of my passion and questions, but engineering and physics have provided me with amazing tools to understand the mechanics of how organisms work. And I really exist at the intersection of these two areas.
Okay. And then what does biomimicry mean to you? Because it seems like there's a lot of different terminology for this sort of being inspired by nature, whether it's biomimicry or biomimetics or bio-inspired design. So have you put much thought into which of these categories you fall into and what that entails?
My general philosophy is to try to extract the essential features from biology in order to apply them to technology. That's the way I look at biomimicry. You have these systems that have been evolving and produce these marvelously inventive solutions to numerous problems that we as humans still have to solve. However, some of these solutions are still constrained by the biology that originated them, the organism's embryology, evolutionary history, or simply its ecology and behavior. So it's important not to simply blindly replicate, but to rather dig down to the true mechanics and physics and underlying basis of the adaptation that we're trying to replicate, and replicate the fundamental core of it without necessarily dragging along some of the inefficiencies that may have been imposed upon the animal simply due to its evolutionary heritage.